All right, guys, let's go ahead and get started. After today, we should be able to tackle most, I would say 90% of the questions. And after today, we'll let you guys loose on trig limits as well. So hopefully today's the day. You can read all that good stuff in the top whenever you guys get a chance. These are your rules about horizontal asymptotes, which you guys already know. It only applies to polynomials. So we're going to be talking about rates of growth. And exponential functions are usually what's growing the fastest, except for factorials. But they're not going to ask factorials, so we're good. All right. Do we have an idea how these look? Letter A, B, and C. All right, guys. E to the x, that graph looks like this. Always, always, always. So, limit as this approaches negative infinity for e to the x is... What does it look like? No. The y value, guys. 0. Uh-oh. we might have issues here. Limit as x approaches infinity for e to the negative x. Do we know how that graph looks? It's 0. And then limit as x approaches infinity for ln x. Infinity. It grows really, really slow. Increasing function. Increasing really, really slow. But it still goes up. Just goes up very, very slow. How do we feel? Do we feel okay, guys? All right. Yeah, those are the three main graphs you got to know to be able to see if you can do the other ones without doing stuff in the calculator. So if you're not very comfortable with those graphs, try to get comfortable with them, guys, please. I think Delta does a really good job. This one I agree. I'm not sometimes I agree with Delta, sometimes I don't agree with Delta, but I think in this one they actually do a really good job of explaining rates of growth. So when you do your Delta math, don't just go to the next one. Please read their notes. Even though you get it right, read their notes because they have a lot of really good stuff in there. All right, so let's see. Now that you know those three, let's see if we can decipher the next ones. So this one says limit as x approaches infinity, ln of ln x. Well, we know this guy here is getting larger and larger and larger, but just very slowly. So now I have ln of that. So it's still going to increase, but now it's increasing even slower. But it's still increasing. Does that make sense? So this again is infinity. All right, here we get to our first test. So I have an exponential function. I see that it's e to the negative x. It doesn't matter how many zeros I have in front, 0.000001x. They eventually all, e to the negative x, will look like that one. Cool? So if I'm approaching infinity, I know that this that I'm circling will eventually be 0. Does that make sense to you guys? So because that will eventually be 0, all of this is going to be 1/2. All that 10 does is a vertical stretch by a factor of 10, but I'm still going to be approaching 0 as x approaches infinity. Does that make sense? Just for that little guy, that term. All right, look at letter F. Do you have to multiply everything? No, we're just looking for end behavior. End behavior of the numerator is 7x squared. End behavior of the denominator is x squared. So my limit is 7. Yay or nay? Yay. All right. Let's look at letter G. As x approaches infinity, what is growing faster, the numerator or the denominator? The denominator, because I have a larger exponent, x squared. So this is going to approach what value? 0. 1 divided by big is 0. They actually use the word big on delta. I think you'll like the notes on delta this time. Because I have some number divided by a big number. The bottom is growing faster than the top. So 1 divided by 1, 1. 1 divided by 10, 0.1. 1 divided by 100, 0.01. You know what I mean? Okay. The bottom is growing faster than the top. What's up, buddy?
So anytime the denominator
Yes. Well, the denominator is growing faster than the numerator as x approaches infinity. So because of that, you're going to have larger numbers in the bottom. So in essence, I have like this effect. 1 divided by 1, 1 divided by 10, which is 0.1. And I know that I'm keeping the numerator constant, but it's the same concept. 1 divided by 100, 0.01. As the bottom gets larger, the output gets closer and closer to 0. Cool? All right, look at this one here. I have an x cubed in the numerator, an x squared in the bottom. It looks like I am unbounded. So this one is going to approach infinity. It does have a slant asymptote, and maybe they would accept that answer, but you know what? No, we're not even going to talk about it. What's up? Yeah, the horizontal asymptote. So it's approaching infinity. It doesn't exist. No, the 25x squared is like spit. If we're talking about spit in ocean.
But if it was 25 times 25x, then you would have to combine those exponents, right?
If it was 5x times 25x.
Yeah, because so
Yes.
So if there's no horizontal asymptote, will it be PNE or will it? So I guess it'll be.
The limit does not exist. It's the same thing as saying the behavior is approaching infinity. If the numerator is bigger than the denominator, the rate of growth, you're unbounded. So the output keeps getting larger and larger and larger. So I keep approaching infinity, which is the same thing as saying does not exist.
Oh, so it'd be like 1 over 1, 10 over 1.
Yes. Letter I. Biggest power is 3 in the numerator. Biggest power is 3 in the denominator. What am I approaching? 7 over 2, 7 halves. Let's see how smart you guys are. That's only if x approaches infinity.
And if they have the same
Degrees, yes. Don't be a robot though. Make sure we understand why, right? Okay. Yeah, well, that's a horizontal asymptote. If I'm approaching a number, that's a horizontal asymptote, and that's approaching positive and negative infinities, right? If I were approaching negative infinity, I would approach the same thing because I'd have negative divided by negative. Look at letter J. Let's see how we feel about this one. You ready, Parker? So here we go. Letter J is a tough one, guys. Well, actually, letter K is the toughest from these, but what do you think the answer is for letter J? Yeah, it is 5. Who said that?
Really?
Yeah. The end behavior of the square root of x squared, you only pay attention to the x squared. The square root of x squared is x, so I have 5x over x, which is 5. Now look at k. It's almost the same. It's negative 5. Make sure we know how we got that one. Yeah, we're about to talk about it. No, we gotta understand the concept behind it of why it's negative 5. All right, yeah, I was about to get to it. Don't worry, miss. All right, guys. So the reason why we have this answer as negative 5, the bottom, the denominator, you're always gonna square it first. So will I ever have a negative inside that square root? No. So the bottom will always be a positive x, no matter what value I have. But the top, I have 5 times some negative x value because x is approaching negative infinity. Does that make sense? So that's why I'm going to get a negative 5 and not a positive 5. Cool or not cool? Okay. So here we go, guys. You know what? Let's make one up. I'm going to make up, let's make up another one. Letter L. Limit and letter M. Same.
I think you're trying to scare us on.
No, I want to make sure that we know. I want to make sure that we know. Okay. Give me letter L and then give me letter M. Let's talk about letter L. X is approaching infinity, correct? Look what you have here. You have e to the negative x, and we know that e to the negative x looks like letter B. Yes or no?
Yes.
So immediately you start focusing on the negative 4x squared and the 3x squared. So what is that? Negative 4/3. Now be careful. Look at letter M. I'm not approaching positive infinity. Now I'm approaching what? Negative infinity. So now my ocean and spit are different. In the numerator, it's still the same. It's still negative 4x squared. But now, which one is growing faster? The x squared or the e to the negative x? E to the negative x. Because look, I'm approaching negative infinity. If I'm approaching negative infinity, that's growing way, way, way faster than any polynomial. Does that make sense? So now I have some number divided by something even bigger. So this is going to equal 0. Something divided by something huge. Do we understand that?
I got lost after the graph.
Yeah. E to the negative x looks like this, right?
Yes.
This is some huge positive number. Huge, huge, huge. It's growing faster than any polynomial. Even x to the 99. So in essence, I have negative 4x squared, which is some big number as x approaches negative infinity, divided by something super huge. Something divided by something super huge is going to be 0, because it's like saying 1 over 1, which is 1, 1 over 10, 0.1, 1 over 100, 0.01. I'm getting closer and closer to 0. The bottom is growing faster. Do we understand that, guys? Okay. If we understand that, then you are in really good shape. No. Well, we need practice, but that's why we're going to get practice with our delta. What's up?
I understand exactly this concept. I just don't see how I would make that switch over. Because I see the exponents, I'm like, I need exponents. Like, I'm not going to see the e negative x.
Well, because you got to see what direction you're going. See, on this one, I was approaching positive infinity. On the other one, I'm approaching negative infinity. So if I'm approaching positive infinity, well, I know e to the negative x is approaching 0.
Oh,
You know?
So for L, you can't really focus on the e to the negative x because it's going towards infinity. And that's the...
Yeah, as x approaches infinity, e to the negative x is approaching 0. So e to the negative x is like spit. It doesn't affect it because it's 3x squared plus some insignificant number, plus practically 0. Because e to the negative x looks like this one, see? So as I approach positive infinity, look, I wrote 0 here. So as I approach positive infinity, this guy is not affecting it. So I'll have to focus on that one and that one. So that's why I got negative 4/3.
Say like this guy's this part, right?
Yes, correct. What's up, Rubio? Okay, what's up?
So hypothetically, if you had a approaching positive infinity, and then you had just e to the x, not e to the negative x, would the e to the x be bigger than any polynomial?
Yes. Yes.
So both approaching negative infinity with the e to the negative x and approaching positive infinity with the e to the x.
If you're talking about what's growing faster, yes. She said, what's growing faster, a polynomial or e to the x as x approaches infinity? And e to the x as x approaches infinity grows faster. But if I approach negative infinity, e to the negative x is growing faster than any polynomial. Cool, guys? All right. Now, oh, what's up? Yes. All right, here we go, guys. When I was writing question number 2 out, I thought I was writing a really good question. But now that I read it, I don't think I've ever seen an AP question say justify with vertical asymptote on a multiple choice. I've seen it on free response, but so now that I read it, I don't think it's a good question. But that's fine. I guess, you know what? Just find all vertical asymptotes. And I know it says justify your work by showing limits, but I think that's a hard way. Let's just talk about why we know it's a vertical asymptote. You guys ready? All right, so I want to figure out all vertical asymptotes. What do I got to do? I got to what? Yeah, factor it out. So in the numerator, what two numbers multiply to give you 6 but add up to 5? So x plus 3, x plus 2. In the denominator, I'm going to factor out an x, and I'm going to notice that I'm going to have difference of squares. So x squared minus 4 is the same thing as? Now that I have that, whatever factor or factors that I have in the top or the bottom that are the same, if they're the same, that's a whole, and if they're not the same, that means whatever I have in the denominator that equals 0, that's a vertical asymptote, correct? Yes. All right, so I see that I have an x plus 2 and an x plus 2, so I have a whole at x equals negative 2, but that's not what I want. What do I want? Vertical asymptotes. Because I have x and x minus 2, I have vertical asymptotes at x equals 0 and x equals 2. What's up?
So if let's say you have like 2x plus 2, so would it not be 1?
Yeah. If I had x plus 2 times x plus 2, then x equals negative 2 would be 1. Like if I had another x plus 2, then yeah, I would. Then I would not have a whole. I would just have a vertical asymptote.
Sorry, where'd you get the 0 from?
Oh, this guy right here. I can't divide by 0. It's by itself, so. Yes.
So it'd be like x minus 2 minus 2.
Yeah. X. Okay, say it again.
Wait.
Are we okay, guys? All right. Here we go. Number 3. Let's see how smart you guys are. We just talked about this one on the first page. What do you think that one is? I don't know.
So when I solved it, I got negative 8. That's not a choice.
No. I focus on the 8x squared in front of the square root, right?
Yes.
And on the bottom, I focus on the x. Before I continue, will the numerator ever be negative? No, because I'm squaring first. So what's my end behavior? In the numerator, it is x square root of 8. For the numerator, that's my end behavior. In the denominator, I'm approaching what? So that's going to be a negative x. Because it's going to be a negative number. Negative 100, negative 1,000, negative 10,000. Cool or not cool?
No, not cool.
The square root of x squared is x.
So why is 8 still in the square root?
Because I haven't simplified it. It's attached to the x squared, so it's part of my end behavior.
I put 8x instead of 8.
Yeah. 8x squared is your end behavior, and it's attached. The 8 is attached to the x squared, and it's inside the square root. Right? I'm approaching negative infinity, so I'm talking about negative numbers. Cool, guys? All right. Chavez, I don't see the answer in there. X's cancel out. 8 is 4 times 2. Negative 2 square root of 2. This is probably considered a hard one. Cool or not cool? Because I'm approaching a negative infinity. So when I'm plugging in x values, I'm plugging in larger and larger negative values. Okay. Parker, are we cool? Okay. All right, guys. So here is where we are probably going to get hurt, not physically. All right, focus, guys. But if we don't know if we don't know the basics of some graphs, it's going to hurt us like in this one. Remember, we have no calculator. So immediately I see that there's nothing I can do there. I mean, if you remember L'Hopital's rule, I guess you can, but you don't know that yet. And you see, actually, no, you can't even do L'Hopital's rule because it's not in determinant form. ln of 1. Do you remember what ln of 1 is? Yeah, see?
No. So that's the thing, like I never learned those stuff.
Yeah.
I don't know when I was supposed to learn those stuff.
In algebra.
Okay. Well, yeah, I never learned those stuff.
ln of 1 is 0. Maybe one of these days we'll have an algebra day, but we can't do an algebra day just yet, guys. So maybe, I don't know, let me know what day you guys are free and we'll do an algebra day after school or something, you know? And I'll post a video up for those that can't make it. So ln of 1 is 0. The graph ln of x looks like this. Yes. Are we okay? Because, well, really, okay, well, really what ln means log base e. And e raised to the 0 is 1. So that's why ln of 1 is 0. Okay. Are we okay so far, guys? Okay. If I'm approaching 1 from the left-hand side, I already know for a fact it's either going to be positive infinity or negative infinity. How do we know that? Because it's a number divided by 0, and we know we can't divide by 0. So I know that my behavior as I approach 1 is either going to be negative infinity or positive infinity. Cool or not cool? All right. Well, let's think about it. If I approach 1 from the left-hand side, I'm looking at the ln of x graph. So if I approach 1 from the left-hand side, do I have positive y values or negative y values? Negative y values. Because I'm approaching, remember guys, at 1 it's 0. So to the left of 1, my y values must be really, really small but negative. So a number in the top, like 1, practically, 0.9 or whatever, divided by a really, 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 really small negative number is going to give you what? Negative infinity.
Oh, because it could be like negative 0.99999.
Yes. So, or negative 0.000001.
Can you go back and explain how, so you said we know that ln of 1 is 0.
Yes.
But then how did you get from there to drawing the graph?
Well, I didn't draw the graph. I just drew the behavior as I approach 1. I know that I'm either approaching positive infinity or negative infinity. I don't know which one. And then I said, as I approach 1 from the left, ln, we know that ln of 1 is 0. So if I approach 1 from the left, ln of 0.9 must be some negative number. ln of 0.99 must be another negative number, really small, negative 0.00001. ln of 0.99999 must be negative 0.0000001.
So your numerator is irrelevant?
In this case, because the numerator is just 1, I'm approaching 1, so it's like 0.9 over something. Do you know what I mean? Are you sure? Okay. What's up?
I'm still kind of confused at like how, kind of like what Kim was asking, like how you found out that it was
Negative infinity?
negative infinity or positive.
Because I know for a fact that I can't divide by 0, and there's nothing I can do in the top. It's not a whole. So as soon as I know that I can't factor anything out, and I know it's not a whole, so it has to be a vertical asymptote. So I'm either approaching positive infinity or negative infinity. Those are my only two options. So then I'm like, okay, what happens if I approach 1 from the left of ln? The ln graph, if I zoom in, to the left of 1, you're below the x-axis. And below the x-axis means my y values are negative. So I have something like some number divided by a really, really small number. Let me see if I can get my calculator to pop up. So here's my calculator now. So you look, watch. Here's my calculator, guys. It took a long time for it to open, but I finally got this guy. So look what's happening. X divided by, and it was ln, right? So I'm not even going to bother with the graph. I'm going to go ahead and just go to second table set and then ask. We don't care. The numerator is just x, right? So if I type in 0.9, that means my numerator is 0.9. But ln of 0.9 is some number that's negative. So if I type 0.9, look, you get negative 8.542. If I type in 0.99, it's going to be a larger magnitude, but more negative. If I type in 0.999, it's going to be another larger magnitude, more negative. Look at that. 0.99999. So that's why I said I'm not saying that the numerator is irrelevant. It's just that the numerator is just going to be this whatever value I put, which is really close to 1. It says 1, but it's not 1. It's 0.999. Do you guys see? So I have some number in the top, like 1 practically, divided by an even smaller and smaller negative value. And that's why I get negative infinity. Does that make sense, guys? Taylor, are you good?
Yes,
For sure.
I think so, yeah.
Parker?
I think it's because I don't know those graphs that I just like.
Yeah, we're going to have an algebra day soon. Look at your schedules, and we'll have a algebra day soon. It's going to have to be done after school, guys, because we're technically behind. So I don't want to use the day for that. Is that cool with you guys? Okay. All right. So look, number 5. Maybe we should have done this one first. Is there anything, before I continue, can I do direct substitution on number 5? No. Is there any way that I can cancel something out? No. So right off the bat, in your head, you should be thinking, I have a vertical asymptote. I'm either going to be approaching one of two answers, either what or what? Perfect. Positive infinity or negative infinity? Yes or no?
So that's because there's a non-removable.
Yeah, you can't cancel anything out. There's nothing you can do. So here's how, let's help you guys out. On the side, I'm going to write 5x plus 1. There's nothing we can do there. And I'm going to factor out a 2, and I'm going to write x minus 2. Are we okay so far? All right, now check this out. Ready, guys? So put your pencils down. Just focus. Just take this in. Okay. Okay, put your pencils down. Just take this in. You guys ready? Look, I'm approaching what x value? 2 from the left. I don't care about the top. I know I'm going to be positive. 5 times 2 is 10. 10 plus 1 is 11. Technically, you're going from the left, so it's going to be a little smaller than 11. We don't care. Why don't we not care? Because I already know the answer is either going to be positive infinity or negative infinity, correct? Because there's nothing. You guys just told me a little while ago that I can't cancel anything out. So I have a vertical asymptote at x equals 2. I'm either approaching positive infinity or negative infinity. Because there's nothing I can factor out. I can't cancel. There's no hole. Not a removable. Are we okay there? Okay, let's start again. In the top, in the numerator, I know I'm going to be real close to 11. I don't care. It's just a number. I know that my output's either positive infinity or negative infinity. In the bottom, I'm approaching 2 from what direction? The left. If I'm approaching 2 from the left, I'm thinking of numbers like 1.9, 1.99, 1.999. Do you guys see that? And if I go 1.9 minus 2, that's a what? Negative number. And as I get closer to 2 from the left, I'm going to get smaller and smaller, but negative. The denominator. Does that make sense? So some number divided by a super, super small negative number is going to be negative infinity.
So you can't do a direct substitution, so you're thinking numbers that are close.
Correct.
You used to get a picture of what it's like?
Yes.
Okay, that's cool.
How do we feel?
I need to write all that down.
Okay, go for it. Gather up your thoughts and hit it up. What's up?
So we're only looking at the x minus 2.
Yes, we're only looking as x approaches 2 from the left. So I'm like, okay, what happens? 1.9, 1.99, 1.999, 1.99999. And I can see that at 1.9 minus 2 is going to be negative. So in the denominator, I'm going to get a smaller and smaller negative number. So some number in the top, like 11 or close to it, divided by a super small negative number, bam, negative infinity. Yeah, I know, it's hard. But you can do it because you're smart.
I have another question.
Yeah, ask.
How do you figure out your vertical asymptote that x equals?
Because you can't divide by 0, and there is not a factor of x minus 2 in the top, so I know it's not a whole. It's not a removable discontinuity. If you can't cancel out a factor, then it's a vertical asymptote.
It would be the same as saying it doesn't exist.
You can say does not exist, but notice that answer choice is not in there. But yeah, you could say does not exist. We just made it harder for you guys. Puarisme?
Yes, thank you.
What's up?
Okay, so I understand that your vertical asymptote is at 2, but I think I'm getting lost in how you start saying, like, it's a number divided by negative.
Yeah. So in the top, see how I have 5x plus 1? So I don't really care about it. I mean, you do care, but you don't care because 5 times 2 is 10 plus 1 is 11. So you can practically say you have like 11. But on the bottom, as you get closer and closer to 2 from the left, you're going to have like a negative 0.1 and a negative 0.01. And what's that? 111, negative 111 or something, and then negative 1,000. You know what I mean? So the bottom just keeps getting smaller and smaller. And this is creating a big number, but negative.
Okay.
Yeah, let me make it like 10.
I see that, but sorry.
No, go ahead.
No, I just how is it?
No, ask. Like,
Okay, so the bottom it's negative 0.1. But I thought you were supposed to be getting closer to 2.
I am from the left. Watch, check it out. I'm gonna go ahead and do something. So check it out, guys. I'm gonna do something for everyone to check out. So what do I have in the numerator? Oh, but what's the expression? 5x plus 1, and then on my denominator, what is it? 2x minus 4. And then I'm going to go to y3. I think I can see all 3 of them. And I'm going to go alpha trace y1 divided by alpha trace y2. So I'm telling my calculator that I'm doing y1 divided by y2. Cool? Now, if I go to table, so let me delete all this. Yes. So check it out. If I put 2, I'm going to get undefined on y3. See? So the y1 is 11 and the y2 is 0 because that's what we just did. So I'm going to get really close to 2, but from the left. So what did we say? Like 1.9? And look, the numerator is going to be some number close to 11. And look at what the denominator is, negative 0.2. And look what I get. Now let me get closer to it. 1.99. And look, the numerator is still just some number. Divided, now I'm dividing by an even smaller number. And look, a larger negative number. 1.999. Bam. Some number. Look, it's getting closer and closer to 11. But we knew that. Divided by, look, negative 0.002. Now that's getting closer to 0. And then some number divided by a really small number, a large magnitude. Look, negative 5,498. It's getting, do you see what's happening? I'm approaching negative infinity. Y3 is the one that we're looking at that behavior. And I just wanted to split up Y1 and Y2 so we could see. So does that make more sense?
It's a lot clearer.
But
It's a lot, yeah.
but you see what we're talking about, right? Did that answer some questions, guys, there? Yeah, keep asking them if you don't understand the concept. The concept is what we're trying to get here. Don't try to make it about formulas. You can still succeed with formulas, but we want to make sure that we know the concepts. Cool? All right, let's see what we got next. All right, now we got these bad boys, bad dudes. Because we haven't been practicing much with trig, and we need to do more trig now. You guys ready? So, from your pre-cal days, cosine squared theta plus sine squared theta equals 1. You know that. You know that. Your mom knows that. Your dad knows that. Your relative knows that. Okay. Your mom knows. I'll stop. All right. So we all know that. I don't know why I even said that. All right. Here we go. Yeah, it is, but I'll leave it there. Why not, right? All right. Yeah, let them. It's all good. So here we go. That's a secant squared. The only way you can get a secant squared is 1 divided by cosine. So divide everything by cosine squared. And we're dividing by cosine squared so I can get that secant squared. So I have 1 plus tan squared theta equals secant squared theta. And it says 1 minus. Well, look, they're being nice to me. Well, kind of nice. So 1 minus secant squared theta is equal to a negative tan squared theta. Cool or not cool? Hopefully you remember, side note, hopefully you remember limit as x approaches 0 of tan of happy face with an x on it divided by happy face with an x on it is equal to 1. Are we still okay? Yes, ma'am. Yes, ma'am. All right. Are we still cool, guys? All right. Here we go. I'm going to expand it. Limit Don't worry, I'll take attendance right now, guys. As x approaches 0, 1 minus secant squared is just negative tan squared. I got to keep the argument. So negative tan squared of 6x over, and I'm going to go ahead and square both of these here. 2 times 2 is 4, x times x is x squared. So are we okay right now? Now I'm ready to go. Now we're all ready to go. Limit as x approaches 0. Giant parenthesis, because we're the limit of all this. Tan of 6x over x times tan of 6x over x times 1 over 4. There it is. All that is the same as what I have in the top. I expanded it. Now it's time to do some chemistry. Okay. Wait. Yes. Are we ready? I need the bottom of these to have the same argument as what the tan has. So what do I need in the bottom of this tan 6x here? Not a 4, I need so I put a 6 in the bottom, so I put a 6 on the top to balance it out. Yeah, I need the insides to match. See? So I needed a 6 here, a 6x, because I need it to be a tan 6x. I need the same thing on the next one, guys. So put a what in the bottom, and then put a what in the top again. Another, yes. So now we are ready. Whatever you see in blue is what I added. This is negative 1, because there's a negative in the front. Then that's another 1, so times 1. Times, and then I guess you can reduce it, but I'll leave it. 36 over 4. And that is equal to, well, yeah, which reduces to, oh, you're good, miss. Negative 9. How do we feel? I'm hoping that this laptop has juice. All right, let's keep going, guys. Oh, ask questions. Do we have questions? Okay, say it again. Where did the what? Where did the 1? Tan x over x is 1.
That's when you did the smiley face, right?
Yes. Yes.
Are they going to give us like the equations on the
No. No equations. No equations, no formulas, no nothing. Yeah, I'm sorry, miss. But you don't need them. There's only one to memorize, sin x over x and tan x over x. And the reciprocals are the same.
Sin x over x is also 1.
As long as x approaches 0, yes.
So it's the same.
If x approaches infinity, sin x over x is 0. Because x is approaching super big. Some number between negative 1 and 1 divided by big.
So tan x over x is 1 and sin x over x is 0?
No, sin x over x is also 1.
But only as it's approaching.
Only as x approaches 0. If x is approaching infinity, sin x over x would be 0.
What about cosine x over x?
That's not a property.
Oh,
Okay, here we go, guys. You guys ready? On this one, can you do direct substitution at the moment? I don't know, Chavez. Do you guys remember what cosecant is? 1 over sine. And so sine of 0 is 0. So that means cosecant, yeah, you can't do direct substitution. So the first thing I would do, I would turn that cosecant into sine. So write limit as x approaches 0 of 3. And then that 4x has to stay down there. And then that cosecant, I'm going to bring it up. Sine 3x. When I bring it up, it's now sine 3x. Are we still okay?
Why did you put the 1 on the bottom and the 1 on the top?
There's no one. What are you talking about?
No, but cosecant is 1 over sine, right?
Yeah, but
Yeah, so that it can be sine again. Because sine over,
1 over cosecant is sine. So,
sorry. Yes. You're good. You're dysfunctional brain.
all right. No, you're good. You're good. We're doing a lot. Are we okay? All right, here we go, guys. I almost, now that I have it as like this, I almost have it where, let's expand it. I almost have it where I can do limit as x approaches 0 of sine x over x, giant parenthesis, 3. I'm going to write sine 3x, and then I'm going to write over the x times 1/4. Maybe I can move the 3 to the other side, so I move the 3 over here. It looks cleaner. Are we okay?
Where did you get the other food from?
I didn't get it from anywhere. I got it. It's that one.
Oh, wow. Okay.
No, you're good, miss. I hope I'm not sounding like. Please ask. I'm just.
I'll ask him.
All right. Yes, Parker.
Is sin x over x the one that
Yes.
okay.
So here we go, guys. What do I need in the bottom of the sine 3x? A 3. If I answered a 3 in the bottom, I got to put a 3 in the. There it is. You're good to go. Now I have 1 times 3 times 3 is 9 over 4, and that doesn't reduce. The answer is 9/4.
Okay, so these, I understand once we get past, like I, well, no, I understand, basically I understand up to when we got to 3 sine x, sine of 3x over 4x, and then from there, I wouldn't know how to whether to do, like, sine 3x over 4 or sine 3x over x.
Well, you have sine 3x, so you got to do whatever the argument you have inside the sine. So I have a 3x, so I need a 3x on the bottom. Whatever you have inside here, that's called an argument, right? So whatever the argument is of your sine, that's what I need in the bottom.
No, but how do you know how to expand it? Like, how do you know not to put sine 3x over 4 and
Oh,
3 over x?
I'm just trying to do sine happy face over happy face. I'm just trying to do that over and over again.
Oh, so you're trying to create that.
Yeah,
So that we have something else to put around one, just like it was.
yeah. So I'm just doing chemistry over and over. Like, oh, I have six oxygens on the left. Oh, I need 6 oxygens on the right. So all we're doing is over and over trying to get sine happy face over happy face, or the other way around, happy face over sine happy face, because that's also 1. You know what I mean? Okay. I'm sorry, say it again? Yes. Are we still cool, guys? All right, here we go on the next one. Can I do direct substitution? You always ask yourself that first. Cosine of 0 is 1, and 1 minus 1 is 0, so you cannot do direct substitution on this one. There's actually a good candidate for L'Hopital's rule, but we don't know that yet. So let's continue with what we do know. So hopefully by now we have enough experience with our algebra and our pre-cal that you are probably saying, well, we've always multiplied by the conjugate of whatever it is that we want to try to get rid of. So we don't want that 1 minus cosine. All right, relax. I see a 1 minus cosine 2x on the bottom, and I know that if I multiply by the conjugate, I'm going to have a 1 minus cosine squared, which can be replaced with a sine squared. So 1, and we've done this. We've done transformations in pre-cal. I know for a fact because I was your pre-cal teacher, and we did this. So here we go. When I do that, here's what you get. You still have the word, you still have a limit. So keep saying the word limit unless you want to do this somewhere on the side. That's fine too. Parenthesis 5x squared. Do not distribute that. Just leave it alone. It'll make life easier for you. In the bottom, that's the difference of squares. I can just write 1 minus cosine squared of 2x. Are we okay? Yes.
When we're multiplying 1 plus cosine 2x in the first part,
Mhm.
we can be positive, like add.
Yeah, because I'm trying to do the conjugate of this because I know that I'll do, if I do that, that's the difference of squares. So I'll have 1 minus cosine squared. I mean, I guess you could FOIL, but the middle terms would cancel out. You know what I mean? Like, watch. 1 minus cosine 2x, 1 plus cosine 2x, 1 times 1 is 1, 1 times cosine x is plus cosine 2x, negative minus cosine 2x, minus cosine squared 2x. These in the middle cancel out. You know what I mean? Conjugate means If that's a minus, change it to a plus. If it's a plus, change it to a minus.
And the purpose of doing that is to get a square so that you can replace it with sine squared.
Yes, because there's a property that says cosine squared plus sine squared equals 1. So that means 1 minus cosine squared is sine squared.
Right.
Okay.
So that becomes your denominator.
Yes. More questions, guys? Hit me. All right. So what's the whole point of this? Let me go. Before I continue, guys, I want to make sure you're not robots. 1 plus cosine over 1 plus cosine, that's just 1. So you haven't changed anything because you just keep multiplying it by 1 all the time. Cool? When I did that, in the denominator, I got 1 minus cosine squared. And we know because cosine squared plus sine squared equals 1, which your mom knows, that means we can replace that with sine squared. Right? So, and I'll stop bringing up moms, guys. I apologize.
That was actually very helpful because I was about to be confused, and then you were like, "Which your mom knows?" Like, "Oh yeah, exactly."
Okay.
That was actually very helpful.
So here we go. Yeah, but I don't know if your mom's gonna appreciate. No, that's it. No more. So here we go. 1 minus cosine squared is the same thing as what? Sine squared. You got to keep the argument. Now I'm ready to expand. Remember, the only thing I know is limit as x approaches 0 of sine x over x is 1. Or it could also be the reciprocal of that. Limit as x approaches 0 of x over sine x is also 1. Are we cool? Sine x over x or x over sine x. It doesn't matter. So here we go. I'm going to expand it. Limit as x approaches 0. And I guess let's start with the sine, right? Sine 2x, and I have 2 x's because of the x squared. X times x sine 2x. So that takes care of the x squared and the sine squared. And the rest I don't care about, so I'm going to write 5, parenthesis 1 plus cosine 2x, close it, over 1 for now, close it.
Wait, okay, so that's the part where I could not recreate that.
Oh, no, yes you can. Yes you can. Look, you see how you have sine squared? So that's the first thing that you should be thinking about. Sine times sine, there's your sine x. There's your sine squared x. And then you see how you have an x squared right there? X and x, so x squared. And then everything else you don't care about, you just group it together.
Okay, so the reason we don't care about it is because the only thing we're looking for is to make it x.
Yes, we're looking for x over sine x. All right, here we go. Everything that's in blue, I'm adding. So I probably shouldn't have drawn that in blue. All right, you guys ready? What does the first x over sine 2x need? A 2. I put a 2 there, then the other one, I need to put a 2 in the denominator. So I'll put it in the one that it doesn't matter, way over there. What does the middle term need, or the middle term product, or whatever? Another 2. So I put another 2 in the denominator. So now we're ready. Equals. You no longer have to write the word limit because now we're evaluating it. 2x over sine 2x. That is 1. The limit of x approaches 0 for that is 1. Then I have another 1. Cool or not cool? Times, let's see, 5, parenthesis. What's cosine of 0? Uh-oh. Yeah, we're going to have to start doing those quizzes for sure. 1. 1 plus 1 is 2. So 5 times 2 divided by, what's 2 times 2? 4. I just substituted. So let's see. How do I get the 2? Right here. It says cosine of 2x, so I plugged in the 0. So that's cosine of 0. Cosine of 0 is 1, and I have 1 plus that. You know what I mean, guys? So what is this? What's my final answer? 5 halves?
Wait, how did you? So cosine x, cosine of x is 1.
No, cosine of 0 is 1.
Yeah, sorry, cosine of 0 is 1.
Yes.
So then when you put 0 in, why?
So-
What happened to the cosine of 2?
Well, it's cosine of 2 times 0, which is 0.
Oh, okay, got it.
Could it also be negative?
No, cosine of pi is negative 1. Oh, you need practice. Practice makes progress. If you just see, if I just see LeBron James play basketball all the time, like, yeah, I get how he dunks. Will I ever dunk? Oh, I don't know. I haven't been practicing. If I practice basketball, I'll get really good. I don't know if I'll ever be able to dunk, but I'll get really good at it. So you just need practice, you know? Do you play any sports? Oh. But anyone who plays sports, when you first played it, you weren't good at it immediately. But the more you play it, the better you get. Number 9. Guys, let's keep going. We're almost done. Number 9. Cosine x minus 1 over 6x as x approaches 9 pi over 4. Can I do direct substitution? Yes. Yes, you can. So and guys, I know we haven't been doing those unit circle quizzes, but they're going to have to start coming up. Yeah. So here we go. Cosine 9 pi over 4 minus 1 divided by 6 times 9 pi over 4. Don't leave it like that. It has an answer. Where is 9 pi over 4? Square root of 2 over 2. Good job. Because remember, 8 pi over 4 is 2 pi, and you're just going another pi over 4. So that's in quadrant 1. Cool? So square root of 2 over 2 minus 1 over, let's see, what's this? That's a 3, that's a 2, 27 pi over 2. We're not going to leave it like that. By the way, on the AP exam, you can leave it like that. But we're not, because we're going to do some arithmetic here. Ready? I'm going to turn that 1 into 2 over 2. So square root of 2 over 2 minus 2 over 2 over 27 pi over 2. And a lot of you can already see what we're doing. Square root of 2 minus 2 over 2 divided, well, I guess I'll slow down. Keep, change, flip. The 2's cancel out, these two specifically. So square root of 2 minus 2 over 27 pi. Yeah, I just did, so I turned the 1 into 2 over 2, and then this is a 2, that's a 2, so I can just do combined like terms. Common denominator. So square root of 2 minus 2 over 2, and then keep, change, flip. This is what I flipped, times 2 over 27 pi. Are we okay so far, guys? You want to take a picture? All right, guys. All right. Yeah, go for it. All right, we're almost done. We just need 2 more. This one I stole from UH. Eventually, you'll just call that a derivative, but we're not there yet. You're going to need one thing. Okay, so let's just get it set up first. So this says that C is pi over 6, so I need f of pi over 6. F of pi over 6. So cosine of pi over 6. Do we know what cosine of pi over 6 is? Square root of 3 over 2. And I need f of pi over 6 plus h. All I'm doing is this. So this is cosine of pi over 6 plus h. Do you remember your composite argument properties? Cosine A minus B.
Cosine pi over 6.
Cosine A. Give me the property first.
So cosine A sine A. Plus cosine B and then cosine B. And then sine. And then
Cosine is cosine cosine.
And then plus sine.
Cosine is cosine cosine. And then the sine is the one that toggles.
I know how it was supposed to look. I just remember.
So here we go. I'm just using that formula up there, guys. Cosine pi over 6 cosine h plus sine pi over 6 sine h. Are we okay so far? Oh, yeah. Yeah, I almost made a mistake there. This one has a plus, so it's a minus on the outside. Yeah, I'll just switch it over here so no one gets confused. plus up here, minus on this one. There, now no one gets confused. Are we okay, guys? Okay, here we go. I guess before I solve it, let's turn these into numbers here. So cosine pi over 6 is square root of 3 over 2. Cosine h minus sine pi over 6 is a half. Sine h. And now I'm ready to do this. Limit as h approaches 0 of this guy, square root of 3 over 2 cosine h minus 1/2 sine h minus square root of 3 over 2, and all this is over h, so catch up to here. That's the f of pi over 6. You know what I mean? I can rearrange this how I see fit, the numerator. So I'm going to move the square root of 3 over 2 to the middle there. So let's see. Limit as h approaches 0, square root of 3 over 2 cosine h minus square root of 3 over 2 minus, is it going to fit, 1/2 sine h all over h. Yeah, I just moved it. Sorry guys, I'll zoom out a little bit. We're almost done. Limit as h approaches 0 on these two terms here. I'm going to factor out a square root of 3 over 2. And you're going to have cosine h minus 1. Should I do it? Yeah, I want to. Over h. And I'm just using my properties, guys. My limit properties that I can separate them like this. There. Can I do that? Okay, you guys don't like it. I won't. If you don't like it, I won't do it. All right, giant parenthesis right here. Are we still okay? Okay. If I'm dividing by one single term like this, there's limit properties I can use, right? Remember my limit properties from a while ago where I give you a table and all that? So I want to go ahead and group this together like so, and I want to group this together like so. Can I do that, guys, or no? Yeah, I can. I don't know if you remember, but if you look at your notes, I want to say it's notes 1, or maybe it's notes 2, for the special properties. You guys, you know what? I still have it in here. Let me see if I have it. Open, and it was. I want to say it was notes 2. Let me see. Yep. Nope. Yep. Nope. Are you here? Yeah, right there. Look at this right there, guys. Do you see this one right here? 1 minus cosine x over x is 0. Well, look what I have right. Oh, man. Look what we have right. Well, I guess I can factor out a negative. Let me put a negative on the outside. And then I'm going to write 1 minus cosine h, because I factor out a negative. So isn't that the same thing as saying 1 minus cosine x over x? And what did that limit say that was? 0. So this right here that I'm circling in blue. Yeah, don't worry. I'm going to go back to it so you can see. I guess, you know what? Let me write the limit outside. Square root of 3 over... Okay, this is a constant, guys. So I'm going to take it out like that. Can I take it out like that? Yeah. Limit as h approaches 0, and I'm making it clean. 1 minus cosine h over h. And then I factor out a negative, so I can write I had cosine h minus 1, but I wanted to write 1 minus cosine h. And, I mean, it doesn't matter because both would have been 0 anyways, but I wanted to look like my formula. 1/2 limit, man, it's not going to fit. H approaches 0, sine h over h. Maybe that almost fit. So this right here that I'm circling is 0, right? Chavez, how do you know? It was one of those formulas that we had. We didn't really look at it. It's number 2. It's this one right here. See, if I put an h here, put an h there, put an h there, that's 0. Do you guys see that? By the way, it's the same thing if I would have written cosine h minus 1 over h. That is also 0, which is what I initially had, which I wanted to leave it. So it's from this formula here. Well, let me erase all this stuff. Well, we just talked about it. We focused on the one that we circled, the sine x over x, on notes 2. Cool?
Yes.
Okay, we're okay? No? All right, Taylor, just take my word for it on this. You see this there? So that just equals 0. Do you agree? Because it's written there, it says 0. Okay. There is a way to do it. I guess maybe we could have typed it into our calculator and see what happens as we get closer and closer to 0, and we'll see that it's 0. All right, here we go, guys. Finally, we're almost done. So this is negative square root of 3 over 2 times 0 minus 1/2 times, what's sine h over h? 1. Good job. So my final answer is a negative 1/2. Sine h over h, which is 1. What happened to the what?
Oh, never mind. I see it.
No, you're good. You're good. Ask. It's all good, miss. Are we okay, guys? Okay. Yeah, maybe we're too ambitious today, but last one. We're still not done. We got one more. All right. Last one. The famous one. All right. You guys ready for this? Okay. Don't worry, guys. It is the last one. This guy is called an epsilon. It's the small epsilon. And this guy is called a delta, the small delta. And the epsilon is like error. And don't worry, well, this is not tested on the AP, but the University of Houston tests it. All right. So what all this means, it says, for the following limit, find the largest delta that works for epsilon equals 0.01. Well, what it means is this. Let me find the textbook so you can see. And I was just looking at it too. Chapter 2. So check it out, guys. Here's my textbook. It's from the Dimana. And it's right there. And I don't know, do you guys understand any of that right there? That it says, assume f is defined in a neighborhood of c and let c and l be real numbers. The function f has limit l as x approaches c. If, given any positive number epsilon, there is a positive number delta such that blah, 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 blah. Do we understand any of it? Huh? We're going to make one, yeah. Don't worry. It's going to be very simple. No, don't.
Are you crying?
All right, look. No, it's going to be very simple. Ready? All right, you guys ready, guys?
I'm laughing at my own joke, and I'm so funny.
All right. All this means, this is just fancy talk for how close must x be to 2, so that's the value that we're approaching, so that x over 3 is within 0.01 of 2/3. That's what it means. I don't know why they make it complicated. Maybe that's the math life. They always want to find a way to make it complicated. So, remember, this is error, right? And I want to be 0.01 away from 2/3, correct? So what I'm going to do is, here's x over 3, which is my function, and I'm going to subtract my 2/3, and I want this error, because it's error, guys, I put absolute value. I want this error to be no more than 0.01. This, on the inside, is what they call your delta. That's your delta. That's all that definition says. Cool, guys?
What do you mean by error?
Error. I want to be within 0.01 of 2/3.
Like your version of it.
Yeah, so 2/3 is 0.67, right? So I will accept between 0.68 and 0.65.
All right.
Cool? All right, so here we go. Absolute value, x minus 2 over 3 is less than or equal to 0.01. I can multiply by 3. X minus 2. As soon as you get it looking like this, what's 3 times 0.01? 0.02, 0.03, 0.03. As soon as you get it looking like this, stop. This is technically what your definition is for delta, because, and I'll show you right now in a little bit. Man, I can't draw that symbol there. Let's see. There we go. That is your definition of what delta is. So this is where you stop. I know, you're like, so what's the point? If a professor were to tell you, give me my x values, give me the x values that will make an error no less than 0.01, then you would keep going and you would say your x values have to be between 2.03 and 1.97. Is that 0.03 from 2? If this were the case, then you would say, oh yeah, any x value between 1.97 and 2.03 will give you this error of 0.01. Now, why is this important? Because of tolerances, right? Like when you're manufacturing something, you want it to be super perfect, but nothing's ever perfect. So you say, we accept tolerance of this to this. The smaller the tolerance, the more expensive, because precision is expensive. Does that make sense, guys? So all that stuff is just, yeah. Taylor, what do you think? Does it make sense now?
It makes more sense, yeah.
Yeah, so when you get to this question, you can stop right here, guys. So all we're looking for is 0.03. And let's see, which one is 0.03? Cool or not cool? How do we feel?